All right, good evening everyone. It's my pleasure to introduce Professor Subhadeep De, today's speaker. So let me give you a very brief introduction. Uh, he did his MSc in physics in IIT Kharagpur in the year 2001 to 3, and then PhD in physics in the University of Groningen in 2004, and postdoctorate in US Maryland University in 2008. And then he joined NPL Delhi, and he has been senior scientist there till 2019. 2019 December he joined IUCAA Pune, where he is a associate professor now. So Professor Subhadeep, they has many interesting research areas like precision measurements using trapped ions and ultra stable narrow line width lasers, optical atomic clock for probing fundamental science, geodesy and technological applications, developing trapped ion based quantum technologies. He has also received a number of recognitions. I will not read all of them, just a couple of them. He is a senior member of LIGO collaboration since 2022, and he is also a member of European Cooperation on Science and Technology in Trapped Ions since 2018, and CSIR Young Scientist Award in Physical Science in 2015. So I just want to mention one more thing that Professor Subhadeep De and Professor Umakant Rapol have proposed a quantum link between IISER Pune and IUCAA. I don't know how many of the students know this. So we all look forward for this quantum link between the two institutes under this iHub Quantum Technology Foundation. So with this brief introduction, I invite Professor Subhadeep De to deliver the
introduction. Talk. Yeah, and I will talk about this link.
Okay.
So good evening, everyone. So as you can see, that title of my talk is Quantum Clock for the Fundamental Science, and the picture what you see here is heart of the trapped ion based quantum clock that we are developing at IUCAA. I'm particularly developing at IUCAA, and IISER Pune, Umakant is developing a neutral atom based optical clock. And I will tell you why these two clocks nearly located, let's say within the Pune city, is very important, and what kind of fundamental science we can do using these two clocks. And the link that was brought up by Mahesh, that is actually will give us the possibility to use these two clocks to explore the fundamental physics, and that's what I am going to start with. Okay, so in my talk I basically have two parts. First, I will start with saying what is the science motivation, why do we want to develop this clock, other than the technological development, that is indigenization of the atomic clock, that's always important, but more like what science can we do after this technological development. And second thing, I will tell you what we are doing right now at my lab, that is Precision and Quantum Measurement Lab, in short PQM lab. So let me start with very basic. So being a human being, we have inquisitive minds, and what do we want to know? We basically want to know everything in the nature. And one fundamental thing that we want to know, that how the universe is made, what are the particles that we have in the universe, and we try to know from the quark level and even before quark level. Yeah. So we want to know how the quark forms the nucleons, then fundamental particles like electrons, how they together form the atoms, and then molecules, and then basically what are the constituent of the different in the entire universe, like different galaxies, planetary systems, everything, which are what and how they are held together. And if we see this entire universe, anything you can, any particle, any molecules in the entire universe, if you think about it, then there are only four fundamental forces which are acting. And these four forces are strong force, which are keeping the nucleons together, then weak force, which are for changing the one quark to another quark, and that is responsible for nuclear decay. Then electromagnetic force, I think all of us know very well about these things, that is like two charged particles, they either repel or attract each with other, that's a Coulomb force. and the gravitational force, like apple falls towards the earth, doesn't fly away. Okay. And then there are a few numbers that the different range that this force work. For example, the the strong force work within the nuclear diameter. This works within the nucleon diameter, and this works basically infinitely. Like if you have a charged particle here and the charged particle anywhere else in the universe, they are attracting, and similarly for the gravitational force. And each of these force have some strength, and these are called fine structure constant. For example, the strong force, we consider it as a relative strength of 1, and electromagnetic force, we know this number, we call it typically fine structure constant, which is 1 over 137. Okay, right? But that number is actually very precise, and there is a fundamental question whether this number is actually constant or not. Okay. So there is a standard model that all of us, let's say, consider to.
Yeah. It's not necessary, but I think you mean the strong force, pi is not the, you mean something else, you mean IUCAA force, is that what you mean, or strong force you mean?
What do you mean?
In the first, do you mean really strong, or the IUCAA, what do you mean?
It's like the nucleons, these are held together.
That is called IUCAA force.
Okay, but that's also like strong force. That's
strong force is called if the quarks, the interaction between the quarks, which is a, so your ranges will be swapped in that case.
Okay, yeah, okay, fine. Thank you for pointing these things out. But the point is like IUCAA, what is the fundamental force? There is IUCAA force is not a fundamental force.
Yeah, that's right.
So what is the fundamental force?
The strong force, but the
Yeah.
pion does not come here.
Okay, so sorry. So I probably I mean, I was putting pion differently, but the fundamental force is not the IUCAA force, that is strong force.
Yeah, that's right.
Yeah, so that's what I basically wanted to mean. Okay, so if you want to describe any particle physics, anything particle which is other than the gravitational force, then there is a very good model that we generally follow, that is called standard model for the particle physics. However, the standard model particle physics have many open questions, all the things we cannot explain. For example, why there is only 6 type of quarks, why there are not in, let's say, different type of quark that we have not invented so far. Why there are only 4 type of force? Why there is not a 5th force? Yeah, there are several open questions, and these 3 forces we can explain by quantum mechanics. However, the gravitational force yet we cannot explain by the quantum mechanics, and the fundamental reason is, one of the fundamental reason is we don't know what is the force carrier there, that is graviton. We know that graviton probably exists, but it's not detected yet. It could be also described by space-time curvatures and so on, so on. So this is left over out of the quantum physics. It's not yet explained by the quantum theory, but rest of these 3 forces can be explained by the quantum physics. Anyhow, the point that I wanted to make here, that there are, even though standard model of the particle physics is a very good model to describe most of the things, but still it cannot describe many of the other things, and we don't have an answer yet to those things. One such problem is constants. Like we know that when we study the physics, we consider several constants in our model, and there are few constants I have written down, and I think all of you are very much familiar with all these constants which we frequently use in our theoretical like modeling and etc. And these are like capital G's, Planck's constant, velocity of light, and so on. So I am not reading all these things. You all know about all these constants, and all these constants what you see here, their values are precisely known, and every year these are getting more and more accurate depending on the measurement systems, and there is a co-data who publishes this value of these different constants, and you can go to this website and you can see what is the latest value of these different constants. However, these constants are dimensional constants, so they have dimensions. For example, velocity of light is speed, which is like meter per second. Similarly, all of them have some dimensions. There are few other constants which are dimensionless constants. Yeah, for example, like coupling constant for electromagnetic force, or any force, strong, weak, any of this force. For example, for electromagnetic force, this is we call fine structure constant, and this is a dimensionless quantity. So you see the value is 137.036, but this goes several digits after the decimal points. Maybe I have it here. Okay, no, probably not. And similarly, there are many other things. So the question is, these constants are actually human defined things. Nature doesn't say that this thing is a constant. that we have defined in our standard model or any other model, like there are also few astronomical constants which doesn't come in standard model, to describe the particles that we see around us. But nature doesn't say whether this should be a constant or not. So it could be that what we call a constant is not necessarily a constant since the beginning of the universe. Then what would be the problem? There will be actually many problems, then our understanding have to be corrected. I will come to that. So it's very important to measure whether these constants are constants or they are actually also varying at a very small rate. It won't change in our daily life, but it will change our understanding about the physics, our understanding of the different things that is going around us.
So just to understand, when you say, if you look at quantum field theory, then they vary, right? You mean vary from different perspective, or what do you mean by vary?
This variation, the origin of the variation can be explained by several ways. Yeah. So for example, as you said, like quantum field theory is only can explain few of these constants, but not everything. For example, gravitational related things, it cannot be explained by quantum field theory. So quantum field theory is one way probably to explain some of the constant, but not for everything. It can be also explained by dark matter and dark energy. It can be explained by vacuum fluctuations. So these all theories what you are saying, these are all theoretical concepts why these constants should vary, and if you talk to theorists from different fields, everyone will give different analogy. But none of these things have measured. Yeah, so what I am saying that we have to measure these things, and then there should be of course theoretical model from particle physics, from high energy physics, from astronomy, from dark matter people and etc. And we have to check which is actually responsible for the variation of this constant. We don't know that.
I see.
You
so
can
just to let me stick to one constant, which is alpha, which is
Yeah.
electromagnetic thing.
Yeah.
There we know how it varies. That is understood from quantum field theory. Are you saying there are more?
Exactly. So you are saying understood from the quantum field theory, but there are other theories which can also explain that.
Like what, sorry?
For example, let's say dark matter, dark energy. You cannot explain by quantum field theory the dark matter, dark energy.
Dark matter or dark energy will not appear in variation of alpha because they don't interact with electromagnetic.
No, that's not true. It can appear. I will come to that thing. I will not explain into these things in detail because that's not really my field, but I will tell you why these things can actually change alpha.
I see. I just
Intuitively.
wanted to know, you said that there are multiple sources that can change alpha.
Yeah, there are multiple, let's say, like, let me give you a different example. Forget about these alpha variations. Like the what we call like standard model of the particle physics, that's only one model. There are several other models which can also explain particle physics. For example, membrane theory or string theory and etc. And there you can explain basically gravity also, right? But standard model is only one theory that generally accepted by most of the people. Similarly, now come.
Just to, I'm sorry.
Yeah.
Other models do not describe particle physics properly, right? Sorry, I'm sorry. I'm missing the context to what you're talking about.
No, what I am saying that there are several theoretical models which explains the particles around us. Yeah, standard. No, that's true. Yeah, why not? Which model? I mean, standard model is not the only model which explains the particle theory.
Okay, maybe you can go on.
Yeah.
I'll talk to you.
So the point what I was saying that similarly as you are saying that quantum field theory can explain the variation of alpha, but that is one way of explaining. There is no measurement. That doesn't say, there is not a single measurement which says this is the only reason why alpha can vary. There could be, it could come from the vacuum fluctuation, it could come from dark energy, dark matter also. Yeah. But anyhow, that's not the really, I mean, also I should say that I am not the right person to explain that theoretical part because that's not my point. My point is the reason what I am telling you is optical clock can measure these things. This is one possible experimental way to measure these things. Anyhow, but as much as I know, I would be able to tell you. So now alpha, fine structure constant, is one of the constant for electromagnetic theory. That's an important thing to measure to understand whether these things are varying or not. And this was first basically predicted, or let's say experimental things were predicted, not the theoretical thing, in 1967 by Buckle and Smith. This is just in one page physical review letter paper where they explained the possible ways of measuring variation of alpha by detecting the quasar absorption spectra. And then they gave some upper limit with the data that was available at that time. This is not the measurement of variation of alpha variations, but that's sort of some upper limit. Now
This is experimental or?
it's experimental. Yeah, so these were some quasar absorption spectra from the telescope that was available in 1967. Then in 1999 actually the experiment started, because at that time the more let us say better telescopes with higher resolutions were available, and then this is an astronomical data, and until let us say last year 2021 you see the improvement of the experimental sensitivity is almost by factor of 2 orders of magnitude, and if you put it in this way, like this is 1 order of magnitude per 10 years, something like that. But these are all upper boundaries of their experimental measurements. None of this actually measured whether alpha is really varying or not. This is only upper bound. This is plus minus error bar. Yeah, so bracket means error bar of this measurement.
So these are the numbers. This is the accuracy up to which they can measure.
Yes, upper bound. So that means alpha, if it is varying, that is varying below of that level. That sensitivity of the measurement. Okay, so now let us see that why alpha should vary. Yeah, and that is sort of coming to explaining that why alpha should vary. Like it seems like you are coming from quantum field theory background, so your explanation will be different and probably will be much more theoretical and mathematical. But as an experimentalist, I try to understand it in a very simple way, and that's what I think probably many of us will be able to understand it in this way, that why alpha should vary. Okay, so this is the alpha, and that is measured, value of alpha in present day is measured up to this level of accuracy, but the point what we are trying to say, probably this number is varying over cosmological time scale. Now if I write alpha, then we can write in terms of electric charge pi permittivity and 1 over h bar times c. So you see all of these things are constant, and the dimension of this first part is exactly opposite, inverse of the dimension of the second part, and that is why altogether it is a dimensionless quantity. Now if I consider one electron, that is a spinning thing, so that should have some flux, magnetic and electric flux, and that is what I have defined in terms of magnetic flux and the electric quantized flux of an electron. Now let us take the second part, this h bar times c, which is a constant as far as we consider. Now this h bar c can be written in terms of this basically phi e and phi m. If I take a partial derivative of these things, then I will get some sort of constant, and then partial derivative of this phi e and phi m with a plus sign in between. Okay, so far so good. Now let us take the entire alpha, that is also a constant. So I can write alpha again in terms of this phi e and phi m, and if I take a partial derivative here, I get a different constant. So this constant is not same as this constant, so I have just not written the detail of it, but here I get a minus sign. But you know that if something is constant, I can make them 0. So if I say this is constant, if I put 0 here, that means my delta phi e by phi is equals to negative sign of delta phi m by phi m. Now if I use this here, that means delta alpha by alpha is non-zero. On the other hand, if I consider this to be 0, then this is non-zero. So one of them have to be correct, both of them cannot be correct. Yeah, so either we have to violate the energy conservation rule, or we have to consider that alpha is varying. That is a very simple way to understand why alpha can vary without going into detail of the quantum field theory or quantum mechanics or astronomical things and high energy physics things. Now both of them cannot be correct, like energy conservation and whether alpha is constant or not. Now let us say if the alpha is varying, or let us say if there is a violation of the energy conservation, what can happen? I do not know what can happen, nobody knows what can happen. There are several theoretical models which will explain it in many different ways, but one possible thing is, like probably this dark matter and dark energy, which is most of our universe, like 95% or so, that percentage is probably not constant. That percentage is also probably changing over a cosmological time since the Big Bang happens. It is a probability, we do not know whether that is correct or not.
I am sorry, just to understand why I know it can change from other perspective, but this too also gives a solution that delta phi is 0 and delta phi m is also 0. That is also a solution.
But that cannot be possible because electron carries some energy. It has a magnetic energy or electric energy both. Yeah. So it cannot be 0, delta phi e cannot be 0, delta phi m also cannot be 0. That is not a possible solution. Mathematically you are right, that is possible. but electron is spinning, so that have a magnetic field, that has an electric field. It cannot be, they cannot be 0.
No, what is delta phi E, please?
This is delta phi E is this quantity, which is basically the electric flux associated to a spinning electron, and since it's spinning, that should also have a magnetic flux. So that's what delta phi m and phi E, and delta phi is change of that thing. Now, under what means?
Change under what? Sorry. I'm just
Delta phi is change in any condition, like if an electron is spinning, whether that is a constant thing, energy of it is conserved or not, and the energy of an electron is two different ways, one is magnetic energy and electrical energy.
No,
So
I
together,
I'm just asking, what does the meaning of delta phi change under what? When you say delta H cross C,
yeah,
you mean what? Is variation under what?
under what? What do you mean by under what?
Meaning
Under time or space.
what-
But
what
Under,
is
it could be both, it could be both. It could be under space and under time, like we have a galaxy here, we have a galaxy few billions of light years ago, and it could be both. So the alpha have a variation over, could have a variation over time, also could have a variation over space. It could be both ways.
so, I don't know. Are there any suggestions that this, if there is a change in alpha, it should be related to Hubble constant or something?
Yes, everything. So that's what is my next slide. So if, like, why do we need to measure alpha is varying in not? How does it matter in our lifetime whether alpha is varying at a very small quantity or not? So the reason is, as I said, one possible explanation you can find from many theoretical things is probably this dark matter and dark energy is not conserved. It's probably also changing. They could be like the quantum nature of the vacuum. The vacuum breaks into electron-positron pair and also annihilates. So that rate is may not be also constant, and why it should not be constant? One possible explanation is probably dark matter, dark energy is influencing this rate of change. Now, if alpha is varying, it could be over space and time both. That means the equivalence principle will also violate. That means, let's say alpha is varying over space. That means alpha on our Earth is different for a alpha which is at like billions of light years away on some other stars. That means the physics principles will be different here and there. So that will violate the like equivalence principle and etc. So basically the point is, it's important if we want to improve upon our known standard model theory and extend possible extension of the standard model, then it's important to investigate on these things. Okay, now what can we do? We have to do measurements to understand whether the theoretical concepts are correct or not.
And I understand. Can you go back to your concept? So when you are measuring, you will also, your measurement will also take into account the middle thing that you have said, right? Everything possible. You are allowing everything possible.
Yeah, we are measuring only whether when anybody will measure, it will not measure that what are the ways it can change. It will only measure the change of alpha.
That is right. So
So far nobody, first of all, so far nobody have measured any variation of alpha. It's only upper bound of the experiments. Now if somebody measures even, they will only measure the change, not the cause. The cause should come from the theorist model, and then it should explain the measurement.
yeah, that is what I'm finding difficult to understand. What I was trying to say, the change in alpha due to the middle thing that you have pointed out, okay?
Yeah.
That is very well understood, how it varies with the energy scale. Okay?
Have anybody measured it?
No, so the point is that if you do an experiment at different energy scale, let's say people are doing it in LHC, and then people will be doing it at some other place.
Now, do you have any example of the experiment at LHC which is measuring alpha variation?
I don't know.
So it doesn't happen. It is wrong. You can take any example, but these examples are not correct.
Sorry, what do you mean not correct?
Like, do you have any example that LHC is measuring alpha variations in that way? I don't have any example.
Sorry, what I'm saying is that the prediction due to middle one,
Yeah,
that's a very certain prediction.
that's a theoretical prediction.
Yes.
Have anybody measured it? And nobody believes on theory until and unless somebody measures it.
Well, people have observed, like standard model that you are saying.
No, people have not observed. People have only explained theoretically, and I am repeatedly saying nobody have measured anything. People have observed. What you call observed means theoretical predictions.
Yeah.
There is no experimental measurements, and until and unless there is an experimental measurement, theory is just a theory. It's a possible way of explanation, like string theory. It's like a string theory. There are lot of theories, but no measurements. Yeah. Okay. So now let's come to the measurement. How can we measure the variations of alpha? There are several ways to measure that thing. One is looking into some events which has happened many years ago. When I say many, like billions of years ago. And what can we do? So basically the point is that event has happened 10 billions or hundreds of billions light years back. This light or electromagnetic wave has traveled on Earth and we have detected it. What astronomy people does, like they detect the radio frequency or visible lights or UV lights, and that photons have actually seen the variation of alpha, if anything has happened, something like that. If there was any at all variation of alpha, that photon have seen a significant variation while traveling that long distance over 100 billions of light years. And one thing of such is looking into the quasar absorption spectra. So the quasars are typically 580 million to 13 billion light years away from Earth, and these spectra, which are either radio frequency or microwave spectra or optical spectra, which comes on Earth, and then there are several detectors, UV detectors, etc. They detect on it, and the typical lines they observed are the iron, charged iron lines, charged magnesium lines, and charged silicon lines. Some of these transitions have a very high dependency on alpha. That means if alpha is varying, those transitions will be highly modified, and one of them is charged iron line. So what people do, people actually measure these spectra, absorption spectra, and then calibrate with the actual iron line on present day and see if there is any significant if there is any difference up to the resolution that they can work on. Okay. The other thing is looking into nuclear reactions. So there is a Oklo uranium mine in Gabon in Africa. So this uranium mine is 1.8 billion years old. That's on the Earth. So our Earth, age of the Earth is around 4.2 billion years or something like that. So that's a natural uranium reactor. Now what people found, the uranium 234 isotope that is naturally available on Earth, it should be 0.72%, but on that natural reactor in Oklo, that is 0.60%. So there is an anomaly. Why that is the case? And that anomaly can be explained by taking variations of alpha. So that was another like measurement that people took, which has actually happened at very long time back, and it could see the variation of alpha if there is any. The other possible measurements are doing some measurements right now and comparing it with some other measurements. So nothing about which is coming something from very past, doing something immediately and comparing between different measurements. And their possibilities is optical atomic clock comparison. So I will explain these things in detail. Second thing is, again, it's an optical clock based on atomic clock, like based on electronic transitions, and the next generation is nuclear clock. The nuclear clock has an advantage, like it's a nuclear transition, so it's much more unperturbed compared to an electronic transition. So sensitivity can be even much further by several orders of magnitude, and dependency of alpha in this case is much stronger. The third possibility is looking into some special atom, like for example dysprosium atom. In dysprosium there are two nearly degenerate states. So these are two opposite parity states which are very close to each other, about 200 Hz difference, 200 Hz in frequency. And one of these state has a strong dependence on alpha, and if we assume that alpha is rate of variation of alpha is 10 to the power minus 15 per year, that means these two states will come close to each other by 2 Hz per year, if I take this as a number. So by very precision measurement of the frequency difference between these two opposite parity states, one can actually give a very good number of whether alpha is varying or not. The fourth possibilities are there are many new proposals coming up by looking into the molecules instead of atoms or nucleus, and looking into the highly charged, and there is a very recent paper just 2 weeks back. So people are trying to make clock using highly charged ions, and they will give much higher sensitivity. Expected is that they will give much higher sensitivity than, let's say, this kind of optical clock that is already, these experiments are already going on.
So you are proposing the first one.
I am, we are proposing this first
So
one.
how time scale comes into picture here?
What do you mean?
So you
Yeah, I'll come to that. I'll explain these things. So not time scale, it's actually frequency measurement. So let me just give you a quick answer. So optical clock can have different applications. One application is using it as a clock and maintaining the time scale. But optical clock can also be used as a sensor to measure these things. Yeah, so here time scale doesn't come, it's a measurement of the precision frequency.
Oh,
Is there a direct variation of alpha with the delta t? As in the cosmic time that you were explaining before, where the times are 1.8 and 13.5 billion years, there I was able to understand that how you are doing the cosmic time scales. But when you're doing it in the exact same time, that will be very, much more finer than that measurement. Right?
Yeah, so I will explain those things, that why this helps. And that one of the answer is related to this slide. So now this side is quasar absorption spectra and the other side is optical clock comparison. And what you see, the plot here is resolution of different optical telescopes, those are used to measure the quasar absorption spectra. And there are several telescopes available worldwide, and the best one, best to best one, have the resolution inverse of the resolution, which is in the unit of delta nu by nu, is on the order of 10 to the power minus 5 delta nu by nu, and resolution is nu by delta nu. Whereas the fractional accuracy of optical clocks have reached to an accuracy of 10 to the power minus 21, few parts in 10 to the power minus 21, and the fractional accuracy is also delta nu by nu. So that means optical clocks is several orders of magnitude higher accurate compared to any telescopes in the world. But then how the quasar works, because they have seen much bigger change, they have travelled billions of light years. Yeah, but still, even if you compare, if you consider that the sort of accuracy that a quasar absorption spectra can reach in today's date doesn't match with optical clock comparison, and I will show you the actual data.
so are you saying that you will measure alpha today and next year and then compare?
Yeah,
Okay.
right. And you probably don't need to do, I mean, if you have enough sensitivity, then you don't need to wait for an year, maybe you can reduce it to months. So then now let me come to the optical clock. I am coming to the optical clock now. I have said enough about the different possible measurements ways for alpha and etc. Let's understand how the optical clock works. It's basically very accurate measurements of a transition frequency, which is not a electric dipole transition, but it's a highly forbidden transition like electric quadrupole or octupole transition. So that means these transitions are very narrow in line width. So you can measure it much more accurately. So you excite the transition, you basically detect the transition by looking into the fluorescence. This is a very simplistic view. Yeah, and then measure basically this transition spectrum, which is supposed to be a Lorentzian sort of things. It could be, considering there are no other broadenings and etc. Then you can measure what is the transition frequency nu 0 with very accurately, and the accuracy will depend on basically natural line width of the transition. And that is the reason you pick up a transition which has a very small natural line width like electric quadrupole or electric octupole transition. Generally the electric dipole transitions have line widths of tens of megahertz, whereas the electric octupole transition have a line width of nanohertz, few tens of nanohertz. So several orders you improve on that. So this is a basic principle how the atomic optical clock or any atomic clock works. So now as you have seen, there are two energy levels which are associated to these transitions, and I hope you remember.
Take transitions which are forbidden up to quadrupole.
Yes, quadrupole, octupole, we are taking octupole.
So up to quadrupole they are forbidden.
Well, quadrupole is also forbidden.
Yeah, that's what.
Yeah, dipole is allowed.
Okay.
Dipole is like you can consider like an allowed transition, which is a very strong transition. Quadrupole and further it's forbidden. So the energy levels, I mean this is just a simple like this atomic theory model. It can be expressed in terms of many things, and it has different terms. The non-relativistic contribution, then finite size of the nuclear corrections like isotope shifts and all these things, and quantum electrodynamic part of it. And if you see the contribution of any atomic level, then 99% basically comes from these non-relativistic contributions, and a very small percentage comes from this finite size corrections, and remaining, that is also very small, that comes from this relativistic QED contribution, which depends on alpha, different exponent of alpha, alpha square, alpha cube, alpha to the power basically infinity. And basically that means if you measure any transition very accurately or any energy level, basically we have to measure transition, then if there is any variation of alpha, that would reflect into your measurement. That is the whole idea. Okay, so what happens? So now I have a 2-level system, that is this clock transition, let us say. So if I write the clock transition, it is in terms of clock frequency and the Planck's constant. Then as I told you in my previous slide that these energy levels have a alpha dependence. So I can simply write this some constant and the alpha dependence part of it, and if I take a time derivative of it, so I am not going into the detail, then for any particular transition I get a sensitivity factor and relative variation of alpha, right, and this sensitivity factor is different for different transitions. That depends on the atomic property, that depends on, if I go back, that depends on how strong this is for a particular energy states or for a particular atomic transition. So for different transitions have different sensitivity factors, and theorists have predicted several different elements starting from neutral atoms, singly charged ion, highly charged ion, nuclear transitions, dysprosium and many other atoms, microwave transitions and molecular transitions, and they have theoretically calculated the sensitivity factor. So basically this factor for different transitions on these elements, but experimentally all of them are not possible to let us say do the experiments with all of them because of the technical issues, because all of these transitions, all of these elements requires laser cooling and trapping and all these things, and lasers sometimes are not available at that particular wavelength, therefore there are several other reasons. So only few of them have actually been experimented, and those are these elements. There are several singly charged ionic elements and there are few neutral atoms, and here you see that ytterbium ion octopole transition, that is a highly forbidden transition, that has the highest sensitivity among those which have been experimented, which for those we can do the experiment in present days. Yeah, so ytterbium ion octopole transition has the highest sensitivity, and strontium that at IISER Umakant is trying to do has very small sensitivity. So that means if we have two clocks, strontium and ytterbium ion octopole transitions, if I compare the change of the transition frequencies over some time scale, it would give me a very good results for the time being that we know today, unless we consider the technology changes in next several years and etc. Also ytterbium ion has another transition which is a quadrupole transition, which is also narrow but not as narrow as the octopole one. So ytterbium ion, comparing two different transitions in ytterbium ion, can also actually give a very good results. So basically the point is, being close to each other, IISER and IUCAA, and having these two clocks, one can actually interrogate these alpha variations very well. So these are the two very good elements for this particular experiment. And now coming back to the I mean, if I put all, yeah,
Why not have two ytterbium ion clocks?
yeah, so we'll do that also, because ytterbium ion is already will be available at IUCAA. So we'll interrogate both of the transitions in IUCAA. Yeah, so you are right, and that is, you are right. So why not having it? I mean, ytterbium ion quadrupole and octopole transition can also give very good result. But ytterbium and strontium can also give very good result, because this is nearly zero variation. Compared to ytterbium other ion, this is plus 88. So the transition slopes will be different. Sorry, the change of slope will be different. Yeah.
So having a low sensitivity is better for.
No, higher sensitivity is better. Higher sensitivity is better, but if you have two elements which have, let us say, nearly zero sensitivity and which have higher sensitivity, then this change can be easily understood.
So the strontium clock will be controlled. Right?
Will be reference.
Reference.
Yes, exactly. So that's the right way of saying. The strontium clock will be a reference, that's not changing over time, but the other element is actually changing over time.
How do you choose these ions or elements?
Sorry,
How do you choose these ions or elements?
how do I choose? Oh, so these all numbers are coming from theoretical models, and this is the like sort of the paper and there are many other papers who told us, the theorists helped us to see ki, okay, this is the transition you should look for, and a bigger table is basically this one. So these are all theoretical numbers of the sensitivities.
So basically, like most of the ions has been explored, and you were showing some of it.
No. Only few of them have been explored. This is a big table on only like let's say 6 or 7 elements have been explored. None of them, rest of those things have not been explored. For example, highly charged ions, it's very difficult to cool them. Molecules, it's very difficult to cool them. There are not lasers available. Some indium ion, which is at a very UV wavelength, 109 nanometer laser, which is not available, so one cannot do.
What is so special regarding ytterbium plus?
Sorry, can you repeat once more?
What is so special about ytterbium plus? Because sensitivity is highest for ytterbium.
That's the atomic property. So that's nature defined. The atomic property is defined by the for a particular transitions, and then so okay, let me tell you exactly why this is enhanced. I don't have an ytterbium ion level scheme. So what happened? This ytterbium, I don't have a level scheme here. So ytterbium ion, the clock transition is F7 state, and this F7 state has a very close opposite parity state. So there is a state mixing, and that enhances this alpha. And this is basically true for all the elements. Like there is something which is like mixing of the opposite parity states, or sometimes it's called what intercombination transitions, and then different p states, they are nearly overlapping to each other, and that gives the enhancement. That's what I call like atomic properties.
Is there anything to do with stability? Because
Which is there anything to do with
stability? Then I mean lanthanides are stable in plastic.
stable in what sense? What stability? Stability of what quantity?
I think he's saying that
You mean radioactivity?
atoms are more stable.
You mean radioactivity?
Not radioactivity, like stability of
Stability of what quantity?
metal ion.
No, say stability of time, stability of frequency. What is the quantity? You mean stability?
States, I think.
States.
Oxidation state, yes.
Here,
No, these are atomic states. So these are perfectly stable. If you consider alpha is not changing, these states are stable. There is no change. If you consider there is no perturbation due to electric magnetic field, these are fixed states. These are atomic states, not motional states. Okay, these are not motional states. Intrinsic property of, and like hydrogen atom, hydrogen alpha line, it's not changing. It's a stable state.
So basically you are saying that coefficient of the higher order alpha terms in the
Yeah,
so
yeah.
it's, strong.
That contributes to the much more strongness of the sensitivity. Yeah.
So higher the transition, I have more sensitivity.
Higher the transition means?
Meaning S to P is lower sensitivity.
Not necessarily. Not necessarily. It's completely the atomic properties. Like for example, the ytterbium ion, that's the transition. That's what we are looking. That is S half. That is the ground state, and the excited state is F7 half, and that is not very high. That is actually the next excited state. But it's only the atomic properties which enhance these things.
you expect the levels to be close to one another.
No, not necessarily. So technical.
But it's in the mixing regime.
Yeah, so this F7 half had a admixture of opposite parity states, and that gives the enhancement. But these two states, like this ground state and F7 half states, they are separated by 467 nanometer wavelength. It's 634 terahertz.
And so,
Say
and
some-
Yeah.
just to understand, when you say sensitivity 0008, as compared to let's say 1, what's the difference? Sorry, I am not getting sense of the numbers.
As compared to 1.
Let's say the sensitivity was
So
1.
that means this number is 0.008, and you have to be careful. These are all theoretically measured number. Yeah, so sorry, theoretically estimated number. So this sensitivity is 0.008, and this sensitivity for ytterbium is 5.91. Forget about the magnitude. Magnitude is only slope.
I see. I understand. So that implies a change in alpha will be more than
Yeah,
that.
the rate of change of alpha. Yeah,
I see.
yeah. You have a question.
So, did you, I mean, you just said something about forbidden transition. Which one was the forbidden transition?
All of them are forbidden transition here. Everyone. So all the clocks are made based on the forbidden transitions only. For example, S to F.
Then I don't get how that is helping in the. I mean, I don't get.
The forbidden.
Transition is necessary.
Yeah. So the forbidden transition means, what is the meaning of forbidden transition? That means you have to drive this transition very hard to excite that thing, and other way of saying that thing, the excited state lifetime is extremely high. For example, the ytterbium ion excited state lifetime is on the order of 3 years. So that means the delta nu is inversely proportional to delta t. So that means delta nu, the natural line width of the transition, is very narrow. So that in ytterbium ion, this is on the order of 3 nanohertz. Yeah. So if you measure a transition which has 10 megahertz line width, that means you can measure that transition with an accuracy of plus minus 10 megahertz. You cannot do better than that. Okay. So now if I put all the measurements, sensitivity of alpha variations, then these are from different things like atomic fountain clock to atomic fountain clock comparison, then optical to atomic fountain clock comparison, optical to optical comparison. These are all the color codes, quasar absorption spectra, the Oklo data, nuclear fission and dysprosium. And don't look into the numbers, because none of them are actually giving any variations of alpha, but look into the error bar size. And you see the atomic clock comparison, the best one is just coming from last year ytterbium octopole and quadrupole transition comparison. Somebody was asking that why don't we do it just ytterbium 2 transition, right? Who was asking that thing? Yeah. So that actually gives the best result so far, and you see the size of the error bar compared to any of them. So optical clock comparison so far gives the most accurate results. However, still it has not reached to a sensitivity level so that it can actually measure the alpha variation. So that means you have to improve upon the clock's accuracy also. And there is a new accuracy which is coming up for the ytterbium clock, that is 10 to the power minus 20 order. Now people are thinking to submerge these things in an cryogenic things to reduce further system errors, and hopefully one day we will be able to increase we will be able to make a better clock, and hopefully we will be able to measure something. But the point here is, like, clock comparison gives the most sensitive results at this moment for this kind of science, and this is only one example. There are many other examples in the fundamental science test using the clock comparison, but I won't be able to go into that thing today. Now, yeah.
Getting more and more towards constant alpha, right?
No. This is sort of sensitivity that you see. These are all clocks, cesium clocks to ytterbium clocks.
Okay, but the here
So,
x-axis is here.
Yeah.
It's going closer to 0.
It's basically 0. You see 10 to the power minus 16. So you cannot see it in this scale. Yeah. So it's like, so even if there is any variation, that should be very slow in rate.
Actually, where the change in alpha is basically coming, because there is no certainty of the levels.
No. No. Sorry, maybe you are right. Yes. Say once again that the.
Because there is a bit uncertainty.
Yes.
That's why this.
Yes. But that change of the uncertainty is very small in rate, provided.
You know from where that change is coming. Like that delta alpha is coming because of the uncertainty of the
State, because of the variation of the alpha, possible variation of the alpha, let's say. Okay. Now coming back to the optical clock in India. So there are 4 places basically people are trying to do the optical clock in India. One is CSIR NPL, where I started the again ytterbium clock project there when I joined there. Then in Pune, myself and Umakant, I am doing the ytterbium ion clock, and Umakant is doing strontium lattice clock. And in IIT Tirupati, Arijit Sharma is doing calcium ion clock, but all of their motivations are different. It's not that everyone wants to do the alpha variation measurement. One thing is technology development, because optical clock is a strategic technology. Even if somebody in the world produces that thing, they won't be able to sell it in near future. Like today we can buy cesium clock, which is 1953's technology. Yeah, but if there is an optical clock tomorrow, which will be probably available in 5 years down the line commercially, but we will not be able to buy that thing because that has a strategic importance. Just to give you an example, like we have a hard time, ISRO have a hard time to buy even rubidium clock for our space technology. They buy it from some company Spectra Time, but they are trying very hardly to develop it within the country, because that is their one of the major, let's say, bottleneck. Like every time buying the rubidium clock which is space qualified is a very difficult thing for the country. Okay, so assume that we have the optical clock in next few years, then we can think of connecting these optical clocks together by this I like to call it quantum link, but this is actually not a quantum, this is a classical link, ultra stable link. And then we, other than the technological development, we can actually do all this kind of fundamental science and quantum metrology and etc. But that is, let us say, a dream, and it will take some time. The easiest, relatively easiest thing is actually connecting the two clocks within the Pune, which are just like 4 kilometers away from each other. And then this link, well, this is just a path, but there has to be a fiber there, and this fiber we do not need to actually put by ourselves. There are already optical fibers available, we have to lend them, yeah. And then we have to do further something on that. So these standard optical fibers won't work, we have to stabilize the fiber. So that is a technical thing, and then we can actually connect these two clocks, provided we develop these two clocks in few years down the line, and we can actually do this kind of quantum metrology and fundamental science to start with within the Pune city.
I am sorry, if I connect two clocks, it will increase sensitivity.
It will give the intercomparison. You see that the strontium has nearly 0 sensitivity and ytterbium has higher sensitivity. So you have to compare these two clocks over time at a very, very stability level, at the stability level of the clock.
I see. I am sorry.
No.
Why do I have to connect? Can I not just make a measurement here and two different labs? And
how do you compare? You have to do the comparison immediately. See, we are talking about sensitivity 10 to the power minus 21, and 10 to the power 21 sensitivity means, if I am putting it in, let us say, layman's language, if supposedly there is a clock which is running for last 300 billion years, our universe is 13 billion years old. Supposedly there is a clock which is running for last 300 billion years, it will give just 1 second inaccuracy. That sort of sensitivity we are talking about. So it is not a clock like a, let us say, handheld device, so that you can just bring the develop the clock in IUCAA and bring it in ISER, or vice versa.
I am just saying, I make a measurement here in another lab and then I have computed data. Can I not just compare?
No. It is not like theoretically computed data. That has to be really compared. The measurement has to be compared. There is no data comparison.
I see.
So the data comparison in real time, the actual measurement. It is not like you are detecting something from the star signals, you simulate and data feed something, and then you go to another lab and compare with that they are fitting. It is not like that. It all depends on, yeah. How do I? By fibers, but not by standard fibers, using standard fibers, but the fiber, I will come to that. These technical things I will come.
The data transfer is very fast. You are saying that the clock sensitivity is like 300 million. Then will the data transfer also be very fast? Can the
No, data transfer has to be very, your point is correct. So within the Pune, let us say this is few kilometers, the data is getting transferred at optical light speed. So it is like nanoseconds order. But you are correct that these two data has to be synchronized also. So you have to truly calculate what is the time takes for a photon to travel from IUCAA to here. And for that, how do you calculate that? You need to know the length. But if your length is varying, if you check just a simple fiber, then fiber length varies. So you have, for exactly for that purpose, you have to first stabilize this length of the fiber at 10 to the power minus 19 level. Otherwise you cannot make these things, okay, my photon will take 1.5 nanosecond to reach from IUCAA to Pune. It could be 1.5 nanosecond, it could be 2 nanosecond also, or something changing. So
ideally, do you want both the clocks in the same room? Ideally.
No.
Ideally.
Doesn't matter.
No. Does it help because you?
No, actually it doesn't help. There is no reason to do that. In fact, it should be, no, actually this should be further separated. It should be as separated as possible. In fact, the clock should be in space.
Why is that so?
Because that is the quietest place. You do not have to think about many systematic things there.
I am talking about the communication delay between the two clocks.
Yeah.
So you want to?
Yeah, we want to. So, well, there are many other things which I am not talking here. For example, this is one measurement, but there are also measurements which are coming from the like the earth spin is also changing, it is not a constant thing. So, how that is varying, that can be like understood if the clocks are further separated. So, the point is like if you want to build a clock experiment, that is a very time consuming and that is also very much money consuming. So, you want to build an experiment which can support many scientific goals, not only alpha variations, right. So, it should be actually further separated if it is possible.
So just a question. So I can also use it to say measure gravitational wave passing by, right?
There are proposals, but at present the clock is not that sensitive to measure gravitational waves.
But if I can make it sensitive,
Then you can, yes, then you can. There are proposals. There are like space based clock proposals, which I mean, you know, if you know about the gravitational wave physics, which I also do not know too much, but there are different frequency bands, and there is a certain frequency band which cannot be captured by LIGO or even Einstein telescopes in the future, and that probably can be captured by atomic clock comparison, but that has to be space based atomic clock.
I see.
Yeah, if you have enough sensitive clock in this space and etc. But there are a lot of questions, so I have like several slides more. So should I cut it down?
10 minutes?
Oh, I see. Okay.
But I hope then there are no questions at the end.
I mean, I have no problem. I can stand here, but I mean, only thing is then I have to complete these things. There are several questions. Actually, I am enjoying, so I have no problem. If you can sit, I am fine. So now, why do we do the optical clock? It's not only for the fundamental science thing. So that sort of I already says, like at present the timing systems, the standard of time is defined with respect to cesium clock, but soon that is going to be redefined. That soon could be in 2026 CGPA meeting or 2030. If does not happen in 2026, then 2013. So, for example, National Physical Laboratory in Delhi, where I was working before, their motivation of developing the optical clock is basically they want to stay at par to the global standard for maintaining the standard time of the country. So, they have to be advanced like the any other advanced countries, and the redefinition will be based on optical clocks. So, that is why NPL wants to develop the optical clock. For us, particularly towards the quantum technology and fundamental science, and I already gave you one example, but there are many other fundamental science that can be captured. For example, you already mentioned gravitational wave. Even with this kind of sensitivity, if somebody can reach on that sort of sensitivity, then it can be detected dark matter, dark energy also. There are all proposals, but these experiments have already been done, like geodesy, orientation and spin dynamics of the earth, and testing standard model like alpha variations or violations of Lorentz symmetries. Then in the future, when you have like the technology is improving every day, like for example, the communication today we use that uses actually 10 nanosecond accuracy of time scale. Tomorrow, if we have the quantum technology, that would certainly require sub-picosecond accuracy of time scale, and that can be only received by optical clock. Microwave clocks won't be able to give that kind of accuracy. So 10 years down the line, for all those applications, I think we are all aware of these things like navigation, communication, cyber security and so on, so on. For example, the communication that we use today will be quantum communication. Yeah, and that would require sub-picosecond accuracy of time scale. So, let us say 10 years or I do not know, maybe 20 years down the line, when the technology improves, then we need much better clocks, and we have to start it from today. We cannot start thinking 20 years after. We are already late. We means India. Okay. So, the pathway would be technology indigenization. That is what we are doing at this moment, and we have started late. Then applications, and these are the applications. Second thing is you can develop the clock which is in the entire big room, laboratory etc. But second thing would be actually miniaturization of that clock. So, you should be able to take the clock and on your hand and would be able to take it to anywhere else. So, that calls building the compact system. But that we should start only once we have demonstrated the technology. We have capability to indigenize each of these things in the lab. And this kind of compact clock also have several applications, like one have to put these clocks in these satellites and space and etc. Today we are placing microwave clocks in the satellites, but tomorrow it will be at optical clocks on the satellite. So, we have to have the deployable systems which can be space qualified or which can be in a 19-inch racks, that sort of things. So, at present worldwide the best clock accuracy is 7.6 times 10 to the power minus 21, and this is a result from February 2022. That is the most recent result. And what is the meaning of this accuracy? That means, as I was saying, if supposedly there is a clock which is running over last 300 billion years, it will miss just only 1 second. The another way of looking into that, if you place two such clocks only 1 millimeter apart in height from each other, it will be able to measure this height difference. Now, who wants to use a clock to measure this height difference? It is actually very important, because there is a worldwide thing going on quantum geodesy. So, we want to map the geodetic things on the earth with the accuracy of 1 millimeter and sub-millimeter, and that is the application where this kind of clocks will be used. So, okay, I am skipping this slide. So, now considering all these things, this our lab, Precision and Quantum Measurement Lab, was established as I joined in IUCAA, and then the motivation particularly for our lab is developing quantum metrology using ultra stable light source, developing the clock and using that for precision measurements like fundamental science, and developing other related quantum technologies which are associated to these ultra stable photons and optical clocks and etc. Okay. So, what do I finally, basically for all these measurements we need ultra stable lights, the photons which are extremely stable in nature. But if some of you are experimentalists and if you have used lasers, you have an idea, if you can buy best commercially available lasers, they are not stable enough, they are all oscillating. If you consider so these laser lights are not stable enough, it has always some mode hopping and etc., and that is not allowed. Actually, I was in this previous slide. So, the typical laser have a stability curve, the Allen deviation is sort of like that, which goes something like this slide probably has some problem. Okay, so let me just not open that slide. Even the best quality lasers, if you buy commercially, that has a stability in 1 second on the order of 10 to the power minus 7, and what we need at least for this kind of experiment is on the order of 10 to the power minus 17 or 18. So, several orders of magnitude down, and how can we do that? So, this is the schematic of what we have to do. It has majorly 3 parts, that is this ultra stable cavity, it is a reference cavity, Fabry-Perot cavity. I think everyone knows Fabry-Perot cavity, but typical Fabry-Perot cavities that we use in the lab, that is not that stable, that is good enough for just locking a laser to do spectroscopy. But here we are talking about stability of these cavities on the order of 10 to the power minus 16. What does that mean? That means if you take earth as a spacer of the 2 mirrors, diameter of the earth as a spacer of these 2 mirrors, then these mirrors are changing its separation with a by few hydrogen atoms diameter. That sort of stability what we are talking about. So, it is not just taking some spacer and putting 2 mirrors on the both sides. Then building the clock, we are doing the trapped ion based clock, that is an absolute reference, and then finally once you produce this ultra stable photons in your lab, it has to be disseminated to another lab, for example IUCAA to Pune, and for that we have to have these fiber stabilization techniques, what we call sometimes quantum channel. Quantum, it is actually not a quantum channel, the quantum, because everything is quantum nowadays, yeah, okay, but it is actually a classical technique, yeah. So, this requires indigenization of the technologies.
Basically,
This
terminals are quantum, right?
the clocks are quantum,
Yeah.
yeah. So, that is why you can say quantum channel, but it is actually a classical technique. So, basically for all these things, these are not readily available things. These technologies have to be indigenized in the lab. You cannot buy this technology even if you pay any price, and that takes lot of time. That is the most time consuming thing. So, I think technically maybe I can skip some of these things, or yeah. So, I would say this one. So, this is for example this ultra. So, let me actually explain this one. So, what if you buy a very good quality laser that will have this kind of mode hoppings and etc., and that typical some numbers are in 1 second, stability is 10 to the power minus 7, which I was saying. Okay, I have to really go quicker before it stops. So, then we need a reference cavity to stabilize them, but still it will be having small drift, and this reference cavity is our design. It is actually involved lot of simulations. I am not going into detail of these simulations. If anybody is interested, he can talk to me separately. So, lot of simulations how to make these cavities stable enough at the level of 10 to the power minus 18 level. So, I am quickly going. So, the sum of the simulations that we have to do to get to that stability is optical simulations, and then there are several parameters in the optical simulations, and thermomechanical simulations, temperature stability and mechanical stability, that is what it means. And we have to do all these parameters extremely accurately, even we have to find out exactly at what point these cavities will be held with an accuracy of plus minus 100 micron. These are called eddy points. So, there are special points where this cavity have to be held, so that it will have minimum deformation and maximum stability. So, you have to find out those points and etc. You have to find out exactly at what length you have to build this cavity with plus minus 50 micron accuracy. So, there are some. So, this is what is plotted here is power available in all higher order. I think these higher order modes everyone knows. We want to basically have almost all the power in the fundamental mode, and that means you have to minimize the power in the higher order modes, and this is our simulated results. You see this we have to scale down by 9 orders of magnitude. So, you have to multiply it with 10 to the power minus 9, so that you can see the higher orders, otherwise there is like only few photons into the higher orders, and that is done by this length optimization techniques. Now, even if you I think many of you probably use the standard Fabry-Pérot cavity in the lab, and why they are not stable? Because they have several vibrations, and the different vibration modes are sort of these are actually calculated number, not animations, not PowerPoint animations, and as they vibrate your mode spacings changes. I think if you have used the Fabry-Pérot cavity using lasers, you have seen the modes appear, disappear, and so on, and that is what it is. For a standard Fabry-Pérot cavity, that looks like here, where the stability is something on the order of 10 to the power minus 3 micrometer, millimeter. If you take an ultra stable cavity, then these vibration numbers are completely different. For example, this mode of vibration is on the order of 10 to the power minus 15. This mode of vibration is on the order of 10 to the power minus 28. This is 28. So, we can just neglect it. We are not at to that level. So, now the same spectrum, if you look for an ultra stable cavity, this is also a movie, but you do not see any change because this is ultra stable, but this is also a movie like this one, and that is actually our, like, after doing all the simulation optimization of the parameters and etc., we have to find out exactly how we have to do it. And like I was saying, we have to know exactly where we have to support these cavities. This is called eddy points, and with what kind of materials, with a simple ball we have to support that, so that it is minimum contact and all these things. Okay, I am not going to detail of that. Temperature stability is another very important thing. Typically in the very good lab, the temperature stability is on the order of 1 degree plus minus 1 degree centigrade. It could be 0.5, but on that order, but that is not enough. So, what do? Our lab is typically on that order. So, we have to do something else, so that the cavity actually does not see the temperature change of plus minus 1 degree centigrade. So, this is like 3 layers shielding, thermal shielding with minimum conduction. So, these spherical ball supports and etc., and then this characteristics time of temperature change is increased to few tens of days, 20 days. So, that means if there is an 1 degree centigrade change outside in the environment, it will take 20 days to make it change inside of the cavity, and then there is an active feedback loop, so that it can correct it within basically millisecond time scale. Then the cavity does not see any temperature change at all. So, this all comes from the simulation results before you actually fabricate the cavity. So, now with all these simulations, we have plotted the stability of our cavity, our design cavity, and you see this is the stability. So, at 1 second we can reach to 2.3 times 10 to the power minus 16 level, and if we integrate further, it saturates to below 10 to the power minus 16 level. And let us compare how this compares with the all other internationally such kind of Fabry-Pérot cavities, ultra stable cavities. So, you see these red dots, these are all room temperature cavities like ours is the green one, and these blue ones are cryogenic cavities. That is a completely different technology. We are not going to do that in the first go. So, if I compare with the red ones, you see this is a green line. So, only few cavities which are slightly better than, these are all in logarithmic scale. So, slightly better than our cavity. The point why it is slightly better, because we are a little bit conservative in one quantity, that is we thought that we can do temperature stabilization at a rate of plus minus 10 millikelvin. But these people, they had, so this is all playing with electronics, and these people, they have done it at 1 millikelvin. So supposedly if we can reach to 1 millikelvin temperature stabilization, our cavities will also reach to this level. But we are a bit conservative, we thought probably we will not be able to do it at 1 millikelvin temperature stability in first go. So that is why we are a little bit conservative here. Okay, so then the optical clock, so finally you have to do this trapped ion based clock thing. So there the ion is actually trapped in an oscillating potential like this. This is called quadrupole trap, and that is how, this is again another thing which we have to indigenize ourselves. This is not something commercially available, and that also requires lot of mathematical things before you are fabricating this thing. Right now we are fabricating, and we are collaborating with RRI Sadiq Rangwala, because they also need a very precision trap. So we came together and developed these things together, and that also involves lot of back end calculations to find out what would be the optimum design, what would be the material, and so on. For example, when you apply some radio frequency to the trap will be slightly hot, and how slightly, it's like millikelvin temperatures, and that slight temperature heating of the trap gives the black body radiation, and that affects, that is one of the major systematic to measure the clock transition. So since we are talking about 10 to the power 18, 19, 21, we have to consider all these small changes, and that is how we have to choose the right material. For example, so the material possible material combinations is copper, chromium, zirconium for the trap body, molybdenum for the trap electrode, and fused silica for the as a insulator. Instead of fused silica, if you use Mecor, which is also a vacuum compatible insulator, then the temperature change of heating is by factor of 2 almost. So instead of 4 degree Kelvin temperature change, it will be 8 degree Kelvin temperature change. So we have to really use fused silica to reduce this black body, and that we got to know only by doing these simulations. Even though this at the end, once you build the trap, then nobody cares, but that requires lot of effort beforehand. So this is how the entire vacuum chamber will look like. It's actually quite compact. It will sit on a 60 centimeter by 60 centimeter thing, and the actual trap will be inside of this vacuum chambers. That is how it will look like, and this trap is under fabrication at this moment. We have rest of the parts already. I will skip these things little bit. Now the fiber stabilization, which is probably interesting to this community because it connects both ISAR and IUCAA. So fiber, if we take a normal fiber, it's not stable. It's changing its length because of the temperature, pressure, and etc. So that means photons, what you see on the other end, they will appear at a different phase, and that's not useful for this kind of precision measurements. So that means we have to stabilize the length of the fiber, so that we always receive photon on the other end exactly same as what we send, with the same phase, same frequencies, and etc. So the phase change of for a particular wavelength, the rate of phase change introduce the frequency change, delta phi by delta t is equals to delta nu. And if I can write this delta phi by delta t in terms of length of the fiber, and if I take different length and 1550 nanometer, which is the communication wavelength, then you see that only few 10 meters of the optical fiber gives instability on the order of 10 to the power minus 16. So if you take only few meters fiber, that is fine, good enough without stabilizing the length, but anything beyond few meters, you have to stabilize the length of the fiber, even within the lab, forget about between ISAR, IUCAA or anywhere else. So for example, this is picture of our lab. So our reference fabricator cavity will be sitting here, and our vacuum chamber and experiment will be here, and if I take a fiber like this, it's on the order of 10 or 12 meter. So even for that, I have to stabilize the length of that fiber, and for that testing as a primary thing, we have actually already built a link fiber between two buildings in IUCAA. So if you can see here, there are actually two fibers. So this goes like that. So there are one pair of fiber which is connected on the other side, and then basically what we can do, we can create a loop, a path of 1.5 kilometer. We have already done that thing. So, we have a 1.5 kilometer long fiber between two different buildings, and first we want to stabilize the length of that fiber as a demonstration. Once we do that, then it is only scaling up. The technology will be basically same. We need the physical fiber between IUCAA and ISAR, then we can stabilize it, which is instead of 1.5 kilometer will be 4 kilometer or maybe 5 kilometer. So, that we are already working on. And then as I said that after this first phase we can already do this actual IUCAA and ISAR thing, but we already have these things which we are working on. Okay, I will. So, last thing, the electronics. So, the most of the electronics that we buy from commercially, they are reasonably well, you can pay more, you can buy, but for us many cases we actually have to develop our own electronics, because we need extremely low noise electronics if we want to reach to that sort of stability. Yeah, so one thing we are also developing, we have actually developed already, this is already ready to use. This is a lock-in PID system. That is a very simple thing, right? We buy it from Stanford Research or anything, lock-in PID systems. But the beauty is this is much more low noise compared to what you can buy from Stanford Research and etc. And it has very nice features also, like touch screens and all these things, and it is completely developed by us. Yeah. So, what you see using these PID systems, this is a typical sort of 1/f noise for a standard very good quality laser, and if we lock using this our own developed system, then we have actually reduced the noise. We have basically washed out this entire 1/f noise at this scale and reduced it by several orders of magnitude, and that is called low noise electronics, and in many of the cases we have to do it ourselves, because that is not commercially available, or even if that is available we cannot just buy it, like it is so expensive and so on, and many times it actually import is not possible. Okay. So, now to develop this entire thing, what I told you, there are several aspects what we have to work on, and I have listed almost all of them, and we have started working on many of them. I gave you some very brief results in few cases, because of the time I could not go into further ones, but the circle ones basically what we are working at this moment, and few things we cannot work at this moment. For example, these lasers, we do not have the lasers. So, until we have the lasers we cannot start the work for those aspects. Okay, I will stop here. So, these are the people who are working in the lab, and this guy is from iHub, supported by iHub. Rest of the people are from Quest, and thanks for listening.
So, the devil is really in the details, right? Okay. So, thank you very much, Professor Subhadeep. Now that we have exceeded the time, what I suggest is we can again.
Yeah, but even this finishes, I can stay longer outside, and you can
so
interact.
Formally we shall
thank
Professor Subhadeep again, and those who are interested to ask questions, they can stay back. Oh yeah, please, yeah, sure.
Or you can come to IUCAA also, because that is just next door. So, please, if you have anything to know, come to IUCAA.
So, I'm sure all of you enjoyed it, and I think it went from fundamentals to little advanced and then more application oriented, and what is actually happening in his lab. I think we really connected at all levels. I suppose all of you agree with me. So, with that I would like to thank very much Subhadeep.
Thank you.
And
Thank
we'll have more sessions,
sure,
and
sure.
you can let me know what kind of sessions you all want.
Yeah.
So, thank you so much.
Thank you.
Yeah.
Thank you.
Thank you. Thank you.